Alright gang, here we go. This is for Chem 2 Unit 9, talking about catalysts. This is the last bit of Unit 9 here. Alright, so we've mentioned before that catalysts increase the rate of reaction. It was one of our main ways that we can increase the rate of reaction, but we never really talked about why that occurs. And so in this video, this is where we're really going to hit the ground running with why do catalysts work the way that they do. Alright, so catalysts increase the rate of reaction by decreasing the activation energy. Okay, so we spent a lot of time a couple videos ago talking about activation energy of reaction, what that means, where does it come from, so on and so forth. And so catalysts will literally change the mechanism. And remember, last video we talked all about reaction mechanisms, how we have these elementary reaction steps that can cause our reaction to go forward. And then if we can introduce some new agent in there that can change things, then we can change that mechanism by which the reaction takes place. And if we change the mechanism, then it makes sense that we should have different reactions, so therefore we'll have different reaction energies, or activation energies. All right. So specifically, we use catalysts because they will lower that activation energy. And by lowering the activation energy, more of our reactant collisions will have enough energy to meet that requirement, and therefore we have a reaction. So here they're doing the decomposition of hydrogen peroxide via bromic acid, it looks like. All right, and so they've got hydrogen peroxide, and this is the uncatalyzed reaction. It just takes place in one step. You get water and oxygen out the other side. And then here you get hydrogen peroxide with these catalysts, okay? Notice that it actually becomes a secondary reaction. You get two elementary steps in here, and so the activation energy for the first step would be from here to here, and the activation energy from the second step would be from here to here. Okay, so we get this new catalyzed reaction because both of these activation energies, this would be your rate determining step because it has the highest activation energy. Okay, but because this is still smaller than this by half, it looks like, maybe less than half, you get a much faster reaction. And then notice that out the other side, we get, these are our reactant, or those are our catalyst molecules, or atoms, ions, you know, that we started with, and we get these same catalyzed ions out the other side. So they're catalysts because they began and ended the same. Now, does that mean at this step here, at this intermediate, that we'll have bromide and hydrogen ion here? No, we will not, probably. Okay, probably these will be in some other way. Catalyst doesn't mean it's going to be the same throughout the entire reaction. It just means that at the beginning and at the end, they're exactly the same. All right. So we've got these three types of catalysts that we're going to briefly talk about: homogeneous, heterogeneous, and enzymes. Okay, pretty simple stuff here. Homogeneous catalysts are when the reactants and catalysts are in the same phase. So if they're both aqueous, or both liquids, or both gases, or both solids, these would be catalyzed, homogeneous catalysts. Okay, and so a lot of times when this occurs is when they're both, the most common homogeneous catalyst is when both the reactant and the catalyst are dissolved in the same solvent. All right, so that same example we just talked about before, where we had the bromide and the hydrogen peroxide decomposition, same idea here. They're taking sodium bromide catalyst, they dump that in, and it started as a solid, so you can see it on the scupula, and they dump it in the hydrogen peroxide solution. Now, hydrogen peroxide isn't pure hydrogen peroxide like the ones you buy in the stores, in between 5 and 10%. Laboratory hydrogen peroxide is usually around 30, but you can buy it higher. But it's only, it's less than 50%, almost always hydrogen peroxide, and the rest of it's just plain water. All right, so hydrogen peroxide is aqueous, and then you dissolve that in there, and then you get this reaction, and this is where your catalyzed reaction takes place. Before you added that catalyst, this was decomposing all on its own. All right. And now heterogeneous catalysts are catalysts that take place in different phases than the reactants. All right, so a lot of times the catalyst itself will be a solid, like a metal plate. This is a super common reaction in and your like your catalytic converter in your car that helps clean up emissions, or your when you get to organic chemistry, you have a lot of this using platinum as a catalyst to help you break down different double bonded and triple bonded molecules. All right, anyway, but so the way it works is, you just imagine, remember, whenever we have this reaction taking place, we have a collision, and the collision needs two things. It needs to be in the correct orientation, it needs to have enough energy. Well, if we take our reactants and make them fixed to something, so imagine that you've duct taped your molecule so it has to be in the correct orientation. All right, then what happens is you have more chance of a higher chance of a successful collision. Right, and so so here you've got hydrogen, and then this looks like your ethene here, your C2H4, is they get attached to this surface, right? And then because of these free electrons that are on this metal, the hydrogen is easier to break up into its two ions. So we can see in the second step, this hydrogen and this hydrogen break off, and then they can collide on either side to break down that double bond that's in there. And then it can just float off the surface and become ethane. All right. So this adsorption of the reactants, this step right here, is usually the rate determining step. Once they're on here, this usually happens fairly quickly comparatively. All right. Enzymes are your biological catalysts. All right. So these are taking place in your body all the time. All right. And they have a region where the reactants attach, and this is called the active site. Okay. And the reactants are referred to as substrates. All right, so for this kind of gross example, once again, they're doing the decomposition of hydrogen peroxide, and they're dumping in beef liver. And beef liver is a catalyst to breaking down your hydrogen peroxide, so it forms water and then your oxygen gas. And you can see this bubbling. It happens really, really quickly. All right, and so this is kind of how it works. So you get this lock and key model where your enzyme is this lock site, okay, and it's got a certain amount of grooves, and then your substrate is this key, and it kind of just slides in there and fits directly into these spots here. And then once it's set in here, it becomes this complex, and this complex allows this thing to become stable and will allow it to just kind of get cut, in a certain way. And then and these two, because now they're stable like this, now it's stable like this, and then it's able to stabilize this transition between the two. All right, and so these enzymes are specific to the substrate. So if your body decides that it needs to do a specific process, it has to formulate and make these enzymes from scratch. All right, so this is kind of an actual molecular model of what's going on. So here's your enzyme, and then here's your substrate, and it just kind of slides right into there in this little hole. Notice that it's it's pretty specific. Not just any substrate would be able to fit into that enzyme. Okay. All right, so here we're going to do this little practice problem here. We're going to take everything we've learned, or most of the things we've learned, and see if we can come up with some of these answers. All right, it says formic acid decomposes in the gas phase at elevated temperatures as following. So here's our formic acid. It becomes carbon dioxide and hydrogen. And this guy is balanced. Awesome. All right, the uncatalyzed decomposition of the reaction is determined to be first order. All right, so that's the red line here. A graph of the partial pressure of formic acid versus time for the decomposition at 838 Kelvin is shown as the red curve. All right, when a small amount of solid zinc oxide is added to the reaction chamber, the partial pressure of acid versus time varies as shown by the blue curve. So here's it with the zinc oxide. All right, so this would be a heterogeneous catalyst, right? Because one's solid, one of them's gas. All right, and we know it's a catalyst because it, vastly increased this reaction time. Instead of it taking over, 2,000 seconds to complete it, completed by like, 900 or so. Anyway, so estimate the half-life and the first order rate constant for the formic acid decomposition. Well, so the half-life, remember, that's how long it takes to become half of what it was. All right, so it started at 300, so half of 300 would be 150. So this is where it reached its, half of what it started at, and so it looks like that happened in about 600 seconds. So we'd say, all right, the T half-life is equal to about 600 seconds. All right, and then it says estimate the half-life of the first order rate constant. All right. So we also know that the half-life of a first order reaction is equal to 0.693 divided by our K value. So that means our K value would be equal to, right, do a little bit of math here, K would be equal to 0.693 divided by 600. All right. And so that's just one of those we derived this several videos ago in our integrated rate laws. All right, so divided by 600. All right, and we get 0.001155. How many sig figs here? Well, just one sig fig, huh? All right, so 1 times 10 to the minus third. All right, and then what would our units be? 1 times 10 to the minus third. Well, it's first order, so that means it would just be inverse seconds. All right, so 1 times 10 to the minus third. Hertz. Inverse seconds. Hertz is more of a physics thing, isn't it? That's no good. All right. B, what can you conclude about the effect of adding zinc oxide in the decomposition? Oh, I kind of already spoiled that one. It's a catalyst, and it'd be heterogeneous because it's solid and the formic acid is a gas. All right. So hetero catalyst. All right. The progress of the reaction was followed by measuring the partial pressure of formic acid vapor at selected times. That makes sense. That's what we graphed. Suppose that instead we had plotted the concentration in units of moles per liter. What effect would this have had on the calculated value of K? Oh, that's kind of a trick question. Well, let's think about how we calculated K. K was equal to the half-life, right? Or 0.693 divided by the half-life. Well, and the half-life was just we measured it once and then again when it was all gone. So if we plotted it as concentration instead of by gas, would that have changed, or by pressure, would that have changed the half-life? No, should have still taken the same reaction, so it still should have taken the same amount of time to go from, where it was to halfway, and so then our K value would have been exactly the same because the half-life would have been exactly the same, so it would be no change. All right. Now, the pressure of formic acid vapor at the start of the reaction is 300 torr. All right, assuming the constant temperature and ideal gas behavior, what is the pressure in the system at the end of the reaction? If the volume of the reaction chamber is 436 centimeters cubed, how many moles of gas occupy the reaction chamber at the end of the reaction? All right. Now, it says we can use ideal gas behavior, so this was, D here. All right, so we can use ideal gas, so we're going to use PV equals nRT, and it says we want to solve for moles, so N is equal to PV over RT. All right, now it says we have the volume, that's 436, all right, so it says the pressure at the start was 300 torr, but it wants us to know what is the pressure at the end of the reaction. Well, the pressure at the end of the reaction, that's pretty easy. The pressure at the end of the reaction, because we've got end of the reaction is when all the reactant molecules are gone and all the products are there, and we get 2 times as many molecules of product as we started with, so that means our pressure should have doubled. So our pressure would be 600 torr. All right. Okay, if the volume of the reaction, how many moles of gas? All right, so that should be everything we need. Okay, PV equals nRT. Now the problem is we have 600 torr. Okay, but I don't have the R value in torr memorized because I'm a bum. All right, so we got to convert this to atmospheres. All right, so for 760 torr, we have 1 ATM. All right, so we'll take 600 divided by 760, and we get 0.789. 0.789 atmospheres. All right, and so that's our pressure, 0.789. And then our volume would be the volume they gave us, 436 centimeters cubed, which is the same thing as milliliters, which is a problem because we need it in liters, so we'll set 0.436. Okay, and then how many moles of gas occupy the, okay, and then the R value, well, because we used atmospheres, we use our 0.0821, and then our temperature is our, let's see, I'm pretty sure 838 Kelvin. 838 Kelvin. All right. So we take our 0.789 times 0.436 divided by 821 times 838. Assuming I didn't fat finger anything in there, the number of moles would be 5.00 times 10 to the minus third. And that would be the moles of gas. Okay. All right. E, the standard heat of formation of formic acid is this. All right. Calculate the delta H for the overall reaction if the energy of reaction for the reaction is 184 kilojoules per mole. Sketch an approximate energy profile. All right. So this is going back to our thermochemistry here. And so we've got our enthalpy of formation. Remember, enthalpy of formation is equal to the delta H of formation of the products. Okay, products minus the delta H of formation of the reactants. All right, and so we'll skip ahead here. Instead of doing it ourselves, we'll just kind of cheat a little bit. Look, they got the same answer we did. Hallelujah. All right, anyway, so here we go. So delta H, and so you got your delta H or your reaction here, your formation of, and they did it backwards. They did the reactants minus the products, but and it's all going to come out the same here. And so then this is the value for this delta H formation of carbon dioxide. Here's the value for hydrogen. Now remember, because that's the periodic, that's how it appears. All right. And so it's elemental form, so it's got a delta H of 0. And then there's the formic acid, which they gave us in the problem statement. We would have had to look this up in the appendix. All right, and then so that's your delta H for your reaction. Okay, so that negative sign tells you that it's an exothermic reaction. All right, and then they drew the energy profile here. So you got your potential energy and your reaction progress. Okay, your activation energy would have been this much here, and so they told us that the activation energy somewhere 184 kilojoules per mole. 184 kilojoules per mole. And then the delta H, notice that they made it an exothermic reaction, so then this delta H value here would have been our 14.9 kilojoules per mole. All right, so that's it. You did it. I'm proud of you. Hang in there. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.